says off. Maybe that's why it wasn't working. Is that better? Okay. I turned it on B anyway. Let me make sure. Yeah. So I was going to give you, to finish up aluminum before I go into titanium, I was going to give you an actual story from January 24th of this year. So it's only 6 weeks old. So a company that I've done some work with that rebuilds the aluminum crankcase housings for aircraft piston engines. So if you got a little Cessna or a Piper or something, it'll have a 4-cylinder or 6-cylinder engine, and it's air-cooled engine. And the crankcase is not cast iron, it's aluminum, because cast iron is heavy and you're going to fly this thing. And the two big manufacturers are Lycoming engines out of where in Pennsylvania, I can't remember, but anyway, in central Pennsylvania, and the other one's Teledyne Continental engines down in Mobile, Alabama. They used to be up in Muskegon, Michigan, but anyway, they moved down to Alabama about 40 years ago. And in any case, they make a bunch of engines, but their engines, a little 4-cylinder engine could cost you $300,000. And a 6-cylinder might cost you $500,000. Well, why are these engines so expensive? Because you're buying a lot of insurance that goes along with them. Okay, if the engine fails, people tend to crash. And when they crash, it turns out people who fly airplanes tend to be on the higher end of the income scale, and they tend to sue when they're dead. Actually, they don't sue, but their families do. And so it's not that these things are really, really hard to make. We're still building them in many ways the way we built them 40 or 50 years ago. And these designs kind of go back to the 1940s. But anyway, you got an aluminum housing, which 2 clamshell halves, and you got a steel crankshaft that goes through the middle, because the steel crankshaft is very heavily loaded. But the aluminum housing really just kind of holds things together, doesn't have much stress on it. So if you want to think of it as, I've got, with a little flange here, I've got an aluminum housing and 2 halves of it. In the middle of this thing, I've got some bearings, and this is my steel crankshaft. And on the end of this, I'll have my piston housings, okay? And they're usually kind of horizontal. So the detonation, the piston is inside here, connected to the crankshaft, and the detonation is in here. You got your spark plugs out here, and so all the stress is on the piston can, okay? Piston head, they call it. But this thing, it just sort of keeps the oil in there. It's, you know, it has the same pressure on the inside as the outside, basically. You know, this is a varying pressure with altitude on the outside, but basically this is the same type of pressure. So it's not pressurized in the basic aluminum housing, and the housing keeps the oil all in so that you can collect the oil and recirculate it through the pump. But all the high stresses are in the piston head and the piston, and on the crankshaft. This is just sort of an envelope to hold everything together. Well, if you went out to buy a new one, it might cost you $30,000 or $40,000 for these 2 halves. So they do develop cracks, and one of the problems in the industry is no one ever throws a part away because they're so expensive to replace. So there's a whole industry out there to repair these things. So let's say you develop a fatigue crack, because these are basically flying fatigue machines. And this is an aluminum casting, and so you weld repair it. Now there's only a few places that you can weld repair it. The Federal Aviation Administration says you must go and do this at a FAA approved repair facility that has proven they have the procedures to be able to do this. And there's actually only a few places that have the procedures to do this. The piston engine companies don't particularly want to have all these mom and pop shops out there repairing things. They would much rather sell you a new one, okay? And they don't like the liability of having one out there that's 40 years old and has been repaired, because if it ever has a problem, they're going to get sued too. So Lycoming and Teledyne are always, they can't stop the repairs, because if you can get approved by the FAA, the original equipment manufacturers can't stop it if the FAA approves it, but they're not exactly happy to have a lot of people extending the life to 40 years. Yes?
If somebody else touches it, doesn't it remove the liability of the manufacturer?
Not to the plaintiff's attorney. The plaintiff's attorney is going to come up with something against everybody. Okay, they're going to make sure their expert has a theory that keeps everybody in, so he can collect a little bit of money from all of them. But yeah, you're right. You would think in the law, supposedly, if it's been altered from its original state, okay, but just to do a little weld repair on one of these things, they can start arguing a design defect. Okay, now the Congress in 1992 passed the General Aviation Revitalization Act, GARA, G-A-R-A, and said, because all the Piper and Beechcraft and Cessna, they were all going bankrupt, and the engine companies were, having some financial problems. So Congress basically says if it's more than 18 years old, you can't sue. Okay, it's not a manufacturing defect if it lasted 18 years. Well, some of the plaintiff's attorneys say, well, if you changed your manual, that's a change. And so now it's no longer, the time starts when you change your manual. Wait a second. You can't update your manual on how to do things? So this is still fighting its way through the courts, and all it does is keep attorneys busy, keeps experts busy, and people just argue all the time. And I put my kids through college. Okay, but it's a very dysfunctional system overall, the whole legal system on some of these manufactured parts. And it's not limited to piston engines. This whole repairs applies to jet engines in a much bigger way. On jet engines, we're talking about General Electric, Pratt & Whitney, and Rolls-Royce engines, okay, that are going in 747s, 737s. It's about a $15 or $20 billion worldwide repair industry to rebuild the engine parts. Because you could have a compressor case that costs $50,000 brand new, and you can repair one for $10,000, okay? It can be a very, very lucrative business to repair things, but again, you have to be an FAA repair station. Anybody who touches this thing and not an FAA repair station, you can go to jail, okay? But there are a lot of counterfeit parts out there too, and that's another problem. Because, I showed you turbine blades that are worth $6,000 a piece. When you scrap a turbine blade, you put a notch in it. You actually grind a notch so that any mechanic sees that and says, oh, I can't install that, okay? To try to keep people from selling scrap parts. Okay, parts that have been scrapped, okay? Parts should be destroyed in some way, even if it's just putting a notch in it, so a mechanic wouldn't reinstall it in an engine. Because you should have a history on some of these things. But anyway, so this company has been in business for about 30 or 40 years. They used to be an authorized repair station for one of the engine manufacturers, and then the engine manufacturer sort of, we don't want to start repairing our own product, we want to sell new ones. And so they sold this, and the family took it over. And Chuck's not part of the family, but he is the chief engineer. And I scratched out his name, you don't need to know his last name and stuff. But anyway, so I'd worked with him before, and one of the problems they had, this is an aluminum casting alloy, and they were using 4043 filler metal. They'd grind out a crack and they'd fill it up with 4043 filler metal. As you'll see as we go along, 4043 is softer. And I just worked with them on an accident that occurred in Canada, and the Canadian Aviation Administration, or Canadian Transportation Safety Board, similar to our National Transportation Safety Board, had investigated the accident, and they said, oh, your filler metal is softer than your base metal, and therefore you have undermatching weld metal, and that's the cause of this fatigue crack. Well, I had to help them respond to that, but in any case, for 30 years, every now and then, someone would go investigate one of these things and find out their weld metal was softer than their base metal, and they say, oh, that's the cause. They didn't go through any fracture mechanics and determine what the stresses were. In fact, I don't know if the original manufacturer knows what the stresses are other than they're low. Okay, it's just a container for oil, if you will, up there, in a sense. No one's really done a big analysis on it, and they don't need to. These things are sort of proven by about 70 years of history. Anyway, a customer had a 3/8 inch stud. You put studs in here into the aluminum housing to hold the piston heads on, and there's, I don't know, there's probably 50 or 60 studs that go through here and stuff and hold the thing together. You got, it's actually not like that. It's actually a stud going all the way through. I just showed the flanges up here. But anyway, you got 40 or 50 studs that hold this thing together and hold the piston heads on. They had repaired one, and someone's torquing the stud, and it's supposed to torque to 204 inch-pounds. And the mechanic's always using a torque wrench here. You never tighten anything on an aircraft engine unless you have a calibrated torque wrench, okay? Particularly on some, it's fatigue loaded. If you don't get the right torque, you're going to get a failure, okay? So anyway, they were torquing it, and it stripped the threads. The stud pulled out, okay? So they tested it. They got it back. They fixed it, did a warranty repair, and as he says, they're moving on. Okay, there were no issues on this other than because no one got hurt. They had to reject the crankcase, but they decided to do a test on their own. As he says, well, we only have a sample size of 2, which is not very big. But what they found is the stud into the base metal, half of the ones failed at 204 inch-pounds. And then the stud into 4043 weld, half of them failed out of 2. With a helicoil and a double helicoil. People know what a helicoil is? A helicoil is if you thread you got a steel stud going into aluminum. And one of the things you can do is you can put a larger thread in the aluminum, and then you have this helical coil that has a diamond-shaped cross-section rather than a spring with a circular cross-section. And you put it in there, and now you have a steel insert in the aluminum with a bigger thread, and then you put a steel screw into this helicoil. Helicoils have been around for 60, 70, 80 years. But it's basically a way to give a larger thread area in the aluminum casting. And a double helicoil, I'm sure, is probably 2 helicoils together, so you get even a larger area. Aluminum's not as strong as steel, and so you're basically trying to make a stronger unit. And the overload average is higher with the helicoils because you have bigger thread area with a larger diameter because of the helicoil insert between the steel and the threads. Anyway, they also made it into 4145 weld metal and got a really big increase in strength. And they thought, as he said to me, you have any ideas? You know, as an engineer, he didn't really know what to do. So I'm going to walk you through what I did when I got this email. And I did all this for free, by the way. I hadn't done the other thing for free for him. But, and that's something I want to point out. If you've taken this course and you graduate and go off somewhere, you're welcome to call me. Because, you know, for all the pain and suffering of having taken the course, you can call me at any time in the future if you run into some sort of problem. I don't mind talking to former students and trying to work you through the problem when you run into a real-world problem of your own. You know, I've said this for years, and I've only had about a dozen students take me up on it, maybe a few more than that, maybe a couple of dozen. And I usually have at least helped head them in the right direction, okay? So anyway, so I'm sort of helping him out on this. Well, first of all, he tells me that it's AMS 4280 alloy. I don't know what AMS 4280 alloy is. This is the Society of Automotive Engineers, SAE. You could call it the Society of Aerospace Engineers, but SAE is the organization for, I think they call it mobility, okay? Whether you're an airplane or a car, SAE essentially writes specifications for that part of the transportation industry, and they have a whole bunch of aerospace material specifications, AMS. So if you're Boeing or you're Lycoming, you're going to specify things under an SAE specification. Well, who knows what an SAE, I mean, there's millions of these specifications out there, but many of them are identical. So you can go to this little book, which is really just an index of all the SAE specifications, and you can come down here. If I blow it up, you can look up 4280. Am I close here? Yeah, 42. I can't even see it. 4280H, okay? And you come aluminum alloy castings, well, at least that sounds right. Permanent mold, that's the way they made the casting. 355 T71. Well, I can recognize that as a aluminum alloy association. 355 is the casting number, T71 is the heat treatment. And I could buy a little 10-page specification from SAE for $59. What a deal. $6 a page, right? This is July 2005. I don't have a newer one, but basically these are all the SAE specifications, okay? You know, with about 25 per page, okay? Great business, keeps those people at SAE going. So now at least I know it's aluminum alloy 355. I had to look it up because he's used to calling it by AMS 4280. Tom Eager doesn't know what that is, so he has to go look it up. That's not too hard. I own the book, okay? And it says the recommended filler metal, if I go to one of these aluminum association charts out of the welding handbook, which I had showed you once before, this type of chart. Under aluminum, if I have 355 alloy welded to 355 alloy, the recommended filler metal is ER electrode 4145. But it's got a few footnotes, okay? They got a lot of footnotes, okay? And one of the footnotes says you could use 4047, another one says you could use 4043. Well, that makes sense. He's been using 4043, so he's compliant. But why would you use 4043? And if you go over to other footnotes on the next page, it says, oh, you could use 409, 410, or 411 filler metal. So I had to go look all that up, which is still in the welding handbook. And here's the compositions. You don't have to worry about all these details, but here's 409, 410, 411, 4043, 4145. 4145 is very highly alloyed. It's got 4% copper, it's got 10% silicon, whereas 4043 is 5% silicon and 0.3% copper. So this is 4043 is lean alloy. That's why it's weaker, okay? And 4045 is highly alloyed. 4009 turns out to be the exact same composition if you check it as 355. Yes? Yes, can. But the aluminum has lots of ductility anyway. But the castings only have 5 to 10% elongation anyway. But it doesn't really matter in this application. You're really fatigue limited, but I'm going to get into that, okay? So it depends on whether it's going to be an overload failure or a fatigue failure. And I'm actually going to walk through some of that. So yes, silicon makes it brittle. It goes to the grain boundaries, but it makes it very fluid, makes the guys in the cast shop love it because it fills the mold and you don't make defective castings, okay? So a lot of your silicon, a lot of your aluminum casting alloys are based on aluminum silicon. So anyway, I've now done a little bit of research and said, well, the recommended is 4145, but you can use 4043, which they've been using since 1976, so it has a little bit of a history, okay? I think they've done about 100,000 of these over the last 40-some years. But, you know, out of 100,000, they probably had a dozen or 2 dozen or something fail. I don't know exactly, but they're not dropping out of the skies. It's a low failure rate, and there's a lot of other reasons why you can have failures. The most recent one I saw is because some mechanic over-torqued the steel bolt, okay? It had nothing to do with the weld, but if you over-torque the steel bolt, you'll get a fatigue in the bolt and you can crash, okay? In any case, so it's okay to use 4043, okay? 4145 gives the highest strength because it's the highest alloy. But if it has higher strength, you're going to get higher residual stresses. You're going to get the, I mean, 4043, you weld it, and if it's the weakest link in the chain, it's going to stretch the 4043 as the metal's shrinking. You'll get stretching of the 4043, and the maximum stress in the weld is going to be at the level of the strength of 4043, right? Whereas if you're 4147 with higher strength, your maximum residual stress is going to be essentially the strength of the base metal, because that's the part that's going to yield. I mean, think of this as a tensile bar made of two different materials, and you pull on it, the stuff that's going to yield in that composite tensile bar is the soft material. And that's going to limit the residual stress to the softer material. So, and then I said, well, if you read the handbook, you can also use these guys. 409 is exact match for the 355. And so no one, if someone comes afterwards and does an analysis, they won't find a difference in composition. And in fact, that's what the Canadian Transportation Board had said in his previous problem of last fall. Oh, you should have used matching filler metal. Well, if you've been doing it successfully for 40 years on 100,000 parts, I'm not sure that's a good conclusion, okay, that your design is wrong, okay? But when people are doing failure analysis on something, they're just looking at something that's different, okay? And they will then jump to the conclusion that that difference is what caused the problem. That's not always true. So after giving that little preface, I said, so what would I recommend? The technical answer for the highest strength is 4145 if I want the highest strength, because it's overmatching filler metal. But I'm not sure static strength is the controlling feature here. It's really fatigue strength. And I told you that usually you would like overmatching filler metal. However, in this particular case, where the thickness is probably 1/4 to 3/8 of an inch, you don't have super high residual stresses, and I think you might prefer in many cases to have undermatching filler metal, because this is not an impact loaded situation and things. You can get a little bit better fatigue strength of softer material. So we were talking about coil tubing before class, and you know, copper is very good for fatigue resistance because it's so soft. It doesn't have much strength, but it's good for fatigue. It can take lots of fatigue cycles. So from a practical point of view, if you got the most experience with 4043, hey, stick with success, right? Yeah. No, go ahead.
I had a question about the castings. I know they do post machine sometimes.
Yep. You can aluminum. You can machine both of them. Yeah, I mean aluminum. Yes, aluminum is soft enough that sometimes it gets gummy, but it usually the high strength is not usually the problem. Usually, the higher strength, the better the chips come off. But I mean, maybe you're right about 70, 75. I haven't ever seen that experience or read that. Usually, 1100 aluminum, the really soft stuff, is what gets gummy. Okay, when you machine. Because it just sort of smears and bonds to the tool and things. Actually, I can imagine in 70, 75 you might think something's gummy, because if you're at the speeds people are machining today, they're going so fast they actually could get a diffusion bond of the aluminum to the steel cutting tool, okay? Because aluminum is very reactive with steel. You generate enough heat and you start coating your cutting edges with aluminum, now you got dull cutting edges. So I think if you're getting gummy on 70, 75, it may be that you're cutting too fast or trying to cut too fast. Okay, but I don't know. I mean,
I've never machined it, but like when I come to shops, they say,
yeah, well, my first comment to them would be slow down. Okay, I mean, but you really need to see it and look at the tool. I mean, you can see if you've done some machining and you've gotten something gummy, and in fact 1100 aluminum, I've ended up stopping and looking at the cutting tool, and boy, I just made a diffusion bond of aluminum to the cutting edge. Well, that's great. No wonder it's dull. Anyway, but the thing is, in machining, back when I was your age, we might machine at spindle speeds of thousands of RPM. Today we're going at tens of thousands of RPM. Literally, the spindle speeds have shot through the roof in the machine shops over the last 30 years. And that's really a result of new cutting tools, better machine performance in terms of when you're going at those speeds, you got to have a lot of precision in how you put the whole thing together. In fact, that's one of the things your dad worked on, right? So anyway, but it's all in the design of that cutting tool. Better materials and better design of the spindles and bearings and everything. Anyway, so if you know, one thing you should do is just, hey, stick with success. And you know, the once every 10 years someone criticizes your undermatching strength, deal with it, which is what they've done. However, 4009 is match composition. It doesn't have too much strength that would give you poor fatigue properties like 4145. You could use 10 or 11 and people would probably have a hard time telling the difference between 409 if they analyze it afterwards. And this gives you some intermediate strength. You've been successful with low strength. You should be successful with intermediate strength. So what would I do? Well, I'd either stick with what you've got, or if you want to change and get rid of this criticism because people say, oh, you don't have the exact same composition. And that's a stupid argument. It means they don't understand welding science and stresses. But people make those arguments. If you want to come up with something matching, I wouldn't go to 4145 because it doesn't match. They're going to give you the same argument on the other side of the strength, right? They're going to say it's not the same. Go with 409. It's permitted under the recommended materials, and it will probably work just fine. So he wanted an advice what he should do. First of all, I'm not going to tell him what he should do. I can tell him what his options are. Okay? Don't tell people what to do because then you're the designer. And if it comes around. Which kind of reminds me of a story. Back when I was I guess I was probably an associate professor. In fact, yeah, I think I must have been an associate. But it's probably an associate. I was an associate without tenure. So this is early 80s, and I was working with a company. This is a division of Johnson & Johnson, and they were looking for some tools, instruments. They made stainless steel instruments for surgeons, okay? Neurosurgeons, general surgeons, you know, scissors, drills, reamers, they made 5,000 different types of hand tools for surgeons, mostly out of stainless steel. But laser, in the early 80s, laser surgery was coming along, and they really wanted something a little bit better. In fact, what they would do is you're cutting some tissue with a laser, and if the laser could have too much power and go through and burn the tissue underneath where you're cutting, and that's a problem. Or if it hits the tool, the surgeon doesn't aim it right, and it hits the tool and reflects off, and now you get a reflection, and the laser now cuts the patient somewhere where you didn't want, okay, because you're just using the surface of the tool as a mirror. Oh, this is not so bad. I mean, these are small little cuts, okay? 1,000 cuts will kill you, but one won't, okay? Anyway, so it's not that bad. So MIT has this industrial liaison program. Johnson & Johnson's a member of it, so this guy comes by, and he was dropping off a sample for me. I was doing some testing on something else. I said, well, what are you here on campus for? He says, oh, I'm going to the physics department to talk to the people about lasers. I said, you are? He says, yeah, what's wrong with that? You think there's, your expression sort of, I said, oh, no problem. Go talk to the people in physics. And he came back about 20 minutes later just shaking his head. And he said, now I understand. Because he explained that he wanted a material that would not reflect and burn the patient in the wrong. And the answer from the guys here in the spectroscopy lab, which was actually at that time it was about 20 yards that way. The head of the spectroscopy lab, this is the world's top spectroscopy lab, knows all about lasers. They said, well, all materials absorb energy from lasers. Yeah, well, some of them absorb 100% of the energy, some of them absorb 1% of the energy, so there's a range in between there from an engineering point of view might make a difference. okay? But you couldn't tell that to a physicist. 1%, 100%, yeah, it's all the same. Okay, in engineering, that could be a difference. So I said, okay, well, John, sit down, tell me what your problem is. And he told me the problem that they wanted to cut the tissue they wanted to cut, they didn't want to burn through beneath that, and they didn't want to reflect. And I said, well, you're posing a problem that is sort of betwixt and between. To have an absorptive material, you want something with no free electrons, because it's the free electrons in a material that re-radiate the energy and cause it to reflect. I mean, what are the best mirrors? Silver, gold, copper, okay? They have lots of free electrons. I said, but if you want something with good thermal conductivity among the metals, you're talking about something that has lots of free electrons. Silver, gold, copper, okay? I mean, so he was actually looking for two. I said, what you need is a composite. I said, it's too bad you can't use aluminum for medical instruments. He says, why not? Well, I thought, you know, they might have some problems. He said, we make lots of instruments out of aluminum. I said, you do? Then you ought to use anodized aluminum, because in anodized aluminum you get a top surface that is an insulator with no free electrons, aluminum oxide, absorbs lots of energy, and then you get the aluminum underneath, which has high thermal conductivity, which will diffuse the heat away. Okay? He says, oh. He says, how do we test that? I said, well, you go out to you make some little discs of aluminum, you go get them anodized, and get them anodized to different thicknesses, and I talked to him about how many microns thick. So he goes out and he gets things anodized 4, 6, 8, and 10 microns. We come back, I find the laser somewhere here at MIT, and we basically hit each one of them with a pulse of laser energy of the same, I think, as a YAG laser, and we just measure the temperature rise of each little disc, and you can figure out how much was absorbed. It's a little calorimeter, right? And we showed that if you didn't have any layer, you didn't absorb any energy, because aluminum's a great reflector. But with an anodized layer, and we showed, I think, I don't remember, I have to go back and look at the patent, somewhere between 6 and 10 microns was sort of the best. And you could I actually sort of calculated that from the wavelength of the light and things. But anyway, we don't have, that's all made sense, okay, in terms of the wavelength of the laser and when you're going to get thick enough to have good absorption and thin enough that you're getting the high conductivity aluminum close to the surface, right? So anyway, the story of this, and the reason I started thinking about this story is they patented it. And I got 2 patents out of this, okay? Hey, you know, good for my tenure. But I got nothing out of it. I've never made a dime on any of my patents, okay? Because the ones that I patented through MIT, no one is using. And the ones I patented through companies, they're all using, but I did it as a consultant, and so they had all the rights. So anyway, I've never gotten any royalties out of any patents. But in any case, when the patent issued, about a year and a half later, all of a sudden I thought, uh-oh, if anyone ever is using this and someone gets burned or, you know, injured, Johnson & Johnson could be sued, but my name's on the patent and I could be sued. So I wrote a letter to Johnson & Johnson and said, I want to be indemnified, okay? That if anyone ever sues you, you will treat me just like one of your employees, and your attorneys that are defending, you know, your other employees who are on the patent will treat me, you know, and take care of me, because I don't want to see hundreds of thousands of dollars in legal costs because Johnson & Johnson gets sued, my name, and I'm an independent consultant. This is one of the reasons for telling you this story. If you're ever an independent consultant, don't be careful about designing things, or design it through an LLC company or something, because if you're the designer, you could get sued. If you're a big corporation, the big corporation will protect their employees, but if you get sued, you can be sued personally, and if you don't have the insurance that, and you can go out and get professional liability insurance. You know how it works? You have to have the insurance in force when the infraction, when you design it, and when the failure occurs. So for $5,000 a year, this was back in the mid-'80s, I could have spent $5,000 on professional liability insurance of $1 million or $2 million or something, and then I would have to carry that for the next 40 years until I die or whatever, right? That didn't sound like such a great deal for something I got no royalties on. So the point of all this is be careful when you actually do design, okay? And the only way someone could have tracked that I designed it is, well, when my name showed up on the patent. Took Johnson & Johnson 6 months, and finally I got a letter from their corporate counsel saying that they would indemnify me. I made about 10 copies of the letter, placed it in all kinds of home, different places in the office, so that if I ever did get involved, I could find a copy of the letter somewhere. Anyway, now the patent's expired, and to my knowledge, we've never been sued. But anyway, just be careful about designing things. I don't know how you guys, actually it might be good to ask your dad what he does, because he designs lots of things, right? If you always do it right, but even if you do it right, okay, you can still be sued even if you're right, and you still have to defend yourself. So anyway, I want to talk about titanium alloys, and anybody have any questions? Okay, titanium alloys come in a number of, well, there's actually not that many titanium alloys. Remember, steel is 1 billion tons a year. Aluminum's 45 million tons a year. Titanium is 165,000 tons a year, of which about 26,000 tons actually go into structural materials. The other goes into, anybody know what the bulk of the titanium is used for? Paint on the walls. Titanium dioxide is in the paint. In ceiling tiles, yes. I mean, titanium dioxide has a higher index of refraction than diamond, and so it sparkles. And so it replaced lead in lead paint for giving you a nice reflective or very white surface, what appears very white because it reflects all the wavelengths of the visible wavelengths.